Chapter 1: A Cosmic Coincidence. Voyager 2's Unplanned Detour. On January 24, 1986, far beyond the warmth of the sun, far beyond the comfort of familiarity, a silent machine passed into the realm of an ice giant. There were no cheers, no live television broadcasts, no dramatic countdown echoing across the world. Voyager 2 did not arrive at Uranus with ceremony. It arrived quietly, after nearly a decade alone. By the time its radio signal reached Earth, it was already history. And yet, what Voyager 2 encountered that day would ripple through planetary science for generations, raising questions that remain unanswered even now. This is not merely the story of a spacecraft, it is the story of a cosmic coincidence. A once-in-a-civilization alignment of worlds, and a planet so strange that it forced scientists to rethink how solar systems are built. Voyager 2 was never meant to visit Uranus. Not originally. When NASA engineers first sketched the Voyager missions in the early 1970s, they were chasing an opportunity so rare it bordered on myth. Once every 176 years, the outer planets, Jupiter, Saturn, Uranus, and Neptune line up in a way that allows a single spacecraft to visit them all, one after another, using gravity itself as fuel. A grand tour of the solar system. Gravity would become the engine, the planets would become stepping stones, and time would be the greatest constraint. Two spacecraft were built, Voyager 1 and Voyager 2. Despite their names, Voyager 2 would launch first, August 20th, 1977. A slender rocket rose from Cape Canaveral, carrying with it humanity's boldest robotic explorer to date. Its mission objectives were ambitious, but specific. Jupiter. Saturn? Their moons, their rings, their storms. Everything beyond that was optional. Uranus was a footnote. A possibility. If everything goes right scenario. Because everything had to go right. As Voyager 2 raced outward, Earth shrank into a pale memory. Days became weeks. Weeks became years. The spacecraft crossed the orbit of Mars, then the asteroid belt, then the domain of Jupiter, the solar system's undisputed giant. In 1979, Voyager 2 survived its first trial. Jupiter loomed like a god of storms, its gravity capable of tearing the spacecraft apart if calculations were even slightly wrong. They weren't. Voyager 2 skimmed past Jupiter and lived sending back images of swirling clouds, volcanic eruptions on Io, and moons that looked nothing like the sterile spheres scientists once imagined. Then came Saturn. The ringed planet revealed complexity on a scale never seen before. Braided rings, shepherd moons, chaotic interactions frozen in motion. But Saturn was more than a destination. It was a decision point. Voyager 2's trajectory could be altered. A slight adjustment, just fractions of a degree, would determine the rest of its life. Turn one way, and the mission would end after Saturn. Turn another, and Uranus would come within reach. This was the gamble. No spacecraft had ever visited Uranus. Not a flyby, not a probe, not even a failed attempt. Uranus was distant, faint, and uncooperative. Even with the largest telescopes on Earth, it appeared as little more than a pale blue disk. No storms, no bands, no drama. Some astronomers quietly questioned whether it was worth the risk. After all, Voyager 2 was already rewriting textbooks. Why push it further? The answer lay in timing. This alignment, the grand tour, would not happen again until the 22nd century. If Voyager 2 didn't go, nothing would. And so, in the quiet rooms of mission control, engineers nudged the spacecraft's path. Saturn's gravity caught Voyager 2 like a slingshot, and Uranus was no longer optional. As Voyager 2 coasted outward, something strange became apparent. Uranus wasn't behaving like the other planets. Even from a distance, astronomers noticed its seasons were extreme, decades of daylight followed by decades of darkness. Calculations revealed why. Uranus was tilted, not slightly, not moderately, but catastrophically. Its axis lay almost on its side, rolling around the sun like a toppled world. a 98-degree tilt. No planet in the solar system came close. Theories emerged quickly. An ancient collision, a rogue world slamming into Uranus billions of years ago, enough force to knock it sideways and leave it that way forever. But these were guesses, speculation. Voyager 2 was the only way to know. By late 1985, the spacecraft was more than 1.7 billion miles from Earth. Commands took hours to arrive. Responses took hours to return. Voyager 2 was operating on its own, executing instructions written years earlier by engineers who could only hope they had anticipated everything. The sun was now a distant star. Temperatures plunged. Power dwindled. Yet the instruments remained alive. Magnetometers, cameras, plasma detectors, all waiting. Then, in January 1986, Uranus grew from a dot into a disk. Still smooth, still deceptively calm. To the naked eye, it looked boring. And that may have been the greatest deception of all, because beneath that serene exterior lay one of the most chaotic planetary environments ever discovered. But Voyager 2 didn't know that yet. It crossed the bow shock, the invisible boundary where the solar wind crashes into a planet's magnetic influence. And instantly the data made no sense. Readings fluctuated wildly. Magnetic field lines twisted at impossible angles. Engineers checked the instruments, then checked them again. Nothing was wrong. Uranus was. As Voyager 2 closed in, the planet rotated in a way that defied intuition. Its poles faced the sun. Its equator pointed into darkness. If Earth behaved this way, entire hemispheres would freeze while the other baked for decades. What kind of world could survive that? What kind of atmosphere? What kind of interior? The closer Voyager 2 came, the more the questions multiplied. And this was only the beginning, because Uranus was about to reveal that it didn't just bend the rules of planetary science, it shattered them. Chapter 2. Unveiling the Tilted Giant. Initial Discoveries. As Voyager 2 closed the remaining distance to Uranus, scientists expected clarity. Instead, they were met with contradiction. The planet filling the frame did not behave like a world should. It rotated, but not upright. It orbited, but not evenly lit. Uranus appeared calm, almost indifferent, yet everything about its orientation screamed instability. The planet was lying on its side. Its north and south poles stretched outward like the ends of a rolling barrel, each taking turns facing the sun for decades at a time. This was not a subtle tilt like Earth's seasons or even Mars' long winters. This was a fundamental rearrangement of planetary geometry, a 98-degree axial tilt that defied every tidy model of solar system formation. From this angle, Uranus did not spin so much as it rolled. And that single fact would influence everything Voyager 2 was about to discover. Before Voyager's arrival, Uranus had always been something of an afterthought. Discovered in 1781, it was the first planet found with a telescope, yet its great distance rendered it elusive. Through Earth-based observations, astronomers saw little more than a bland, featureless disk tinted faintly blue-green by methane in its atmosphere. No swirling storms like Jupiter, no dramatic rings like Saturn, no obvious heat signature. Uranus, it seemed, was quiet. Voyager 2 was about to reveal that this apparent calm was not simplicity, but disguise. As the spacecraft approached, its instruments began measuring sunlight reflected from Uranus's upper atmosphere, and immediately something felt wrong. The planet was absorbing far more energy at some latitudes than others, yet it was not redistributing that heat the way other gas giants did. On Jupiter and Saturn, internal heat rises from deep within, driving massive storms and jet streams. Uranus, by contrast, appeared almost thermally dead. There was little excess heat escaping from its interior. It was as if the planet's engine had shut down long ago. Scientists struggled to explain how a world of Uranus's size and mass could be so inert, so quiet, so cold. This lack of internal heat would later become one of Uranus' greatest mysteries, but at the time, it only deepened the sense that this planet was an outlier. The tilt complicated everything. Because Uranus was lying sideways, its seasons were extreme beyond anything previously imagined. One pole basked in continuous sunlight for over 20 years, while the other remained locked in darkness. Then the roles reversed. Voyager 2 arrived at a particularly strange moment. The southern hemisphere was facing the sun almost directly, while the northern hemisphere was plunged into a prolonged winter night. This meant that the spacecraft was not observing a balanced world, but a planet caught in seasonal imbalance, frozen into a configuration that could not represent Uranus as a whole. What Voyager saw was only a snapshot, but it was a snapshot taken at one of the most extreme seasonal angles possible. At first glance, Uranus's atmosphere appeared smooth, almost lifeless. The cameras returned images of a pale cyan sphere with only the faintest hints of cloud structure. For a mission that had just witnessed Jupiter's raging storms and Saturn's intricate ring shadows, this was underwhelming. Some scientists worried that Uranus simply had nothing to offer visually. But Voyager 2's instruments were not limited to human vision. As image processing improved and contrast was enhanced, subtle details began to emerge. Thin cloud bands, wispy streaks, faint atmospheric circulation patterns moving at surprising speeds. Uranus was not featureless, it was restrained. Its weather operated quietly, efficiently, without spectacle. Then came the rings. Before Voyager, Uranus was known to possess a ring system, but it was assumed to be faint, narrow, and unremarkable. Saturn's rings dominated the imagination, so bright and massive they could be seen from Earth. Uranus rings, by comparison, were expected to be thin leftovers, barely worth attention. Voyager 2 shattered that assumption almost immediately. As the spacecraft passed behind the planet, its instruments observed starlight blinking on and off in precise intervals. These were not random fluctuations. They were shadows cast by rings, many more than expected, arranged in a complex system of narrow, sharply defined bands. Unlike Saturn's icy brilliance, Uranus rings were dark, almost black, reflecting very little sunlight. They were composed not of clean ice, but of radiation-archened material, possibly the remnants of shattered moons, ground down and coated by time. The discovery of these rings raised uncomfortable questions. Dark rings should not last long on cosmic time scales. Collisions, radiation, and gravitational spreading should disperse them. Yet here they were, stable and sharply confined. Something was maintaining them. Voyager's data hinted at the presence of small Shepherd-Moonsteiny satellites whose gravity corralled the ring particles, keeping them locked in place. These moons were too small to be seen clearly at first, but their influence was unmistakable. Uranus, it turned out, was not a simple system at all. It was an intricate balance of forces, quietly maintained in the dark. As Voyager 2 drew closer, the illusion of calm continued to erode. The planet's atmosphere, while subdued, exhibited winds blowing at hundreds of miles per hour. Methane absorbed red light, giving Uranus its blue-green hue. But beneath that veneer lay layers of hydrogen, helium, and complex hydrocarbons shaped by an environment unlike any other planet Voyager had encountered. The extreme axial tilt meant that atmospheric circulation did not behave predictably. Solar energy was dumped unevenly across the planet, and yet Uranus somehow avoided the violent chaos this imbalance should have caused. It was as if the planet had found a way to cope with instability through restraint. And then there was the growing unease among the magnetometer team. As Voyager 2 continued its approach, the data became increasingly erratic. The magnetic field readings refused to align with Uranus's rotation. They drifted, they twisted, they pulsed. At first, scientists suspected interference or calibration errors, but the pattern persisted. Something was deeply wrong with Uranus's magnetic environment, and whatever it was, it would soon become impossible to ignore. By the time Voyager 2 reached closest approach, it was clear that Uranus was not merely tilted. It was fundamentally misaligned. Its rotation, its seasons, its rings, its atmosphere, all were shaped by a history far more violent and complex than its placid appearance suggested. The planet that once seemed dull had revealed itself as one of the most unconventional worlds in the solar system, And yet, Voyager 2 was only beginning to understand just how strange Uranus truly was. Because the next discovery would challenge not just assumptions about Uranus, but the very nature of planetary magnetic fields. Chapter 3, The Magnetic Enigma, a Sideways Field. By the time Voyager 2 crossed fully into Uranus' magnetosphere, the mission team already knew something was wrong. The data arriving from the magnetometer did not resemble the clean, symmetrical signatures seen at Earth, Jupiter, or Saturn. Instead of a magnetic field neatly aligned with the planet's rotation, Voyager 2 recorded a chaotic pattern that seemed to twist, lurch, and reorient itself as Uranus turned. At first glance it looked like noise, the kind of erratic behavior engineers dread, but the signal was persistent. It repeated. It followed the planet's rotation. Uranus was not magnetically broken. It was magnetically bizarre. On Earth, the magnetic field emerges from deep within the core, aligned roughly with the planet's spin axis. The same is true, more or less, for every magnetized planet known at the time. Even the gas giants with their fluid metallic interiors obeyed this rule. Uranus did not. His magnetic field was tilted by nearly 60 degrees relative to its axis of rotation and, even more disturbingly, was offset from the planet's center by thousands of kilometers. This meant that as Uranus spun, its magnetic field did not rotate smoothly. It wobbled. It swept through space like an unbalanced gyroscope, dragging charged particles along with it in a constantly changing configuration. The consequences of this misalignment were profound. Instead of a stable magnetosphere forming a protective bubble around the planet, Uranus's magnetic field created a shape that was stretched, compressed, and twisted by both rotation and solar wind. At times, the magnetotail, normally extending neatly away from the sun, wrapped itself around the planet in a corkscrew-like motion. Charged particles were funneled into regions no model had predicted. The magnetosphere was not simply tilted. It was alive, dynamic, and violently asymmetric. Voyager 2's instruments recorded intense bursts of radiation where none were expected, followed by eerily quiet regions where charged particles seemed to vanish. Plasma waves oscillated at strange frequencies. Auroral activity, typically confined near planetary poles, appeared in unexpected locations, sometimes far from where the magnetic poles should have been. On Uranus, the concept of a magnetic pole itself became slippery. The poles wandered through space as the planet rotated, describing vast loops rather than fixed points. For scientists accustomed to orderly magnetic geometry, this was deeply unsettling. The mystery deepened when researchers attempted to identify the source of the field. On Earth, a molten iron core acts as a dynamo. On Jupiter and Saturn, metallic hydrogen performs a similar role. Uranus, however, lacked the mass and pressure needed for large-scale metallic hydrogen. Its interior was thought to consist mostly of water, ammonia, and methane substances that, under extreme pressure, behave in exotic ways. Voyager 2's findings suggested that Uranus's dynamo did not sit at the planet's center at all. Instead, it appeared to be generated in a relatively thin shell, offset from the core, producing a lopsided field that no longer respected symmetry. This realization forced scientists to confront an uncomfortable truth. Their models of planetary magnetism were incomplete. Uranus demonstrated that a magnetic field did not require a neat centralized engine. It could arise in strange places, under strange conditions, and produce results that defied intuition. The planet's sideways rotation only amplified the chaos. Because Uranus lay on its side, the orientation of its magnetic field relative to the sun changed dramatically over the course of a single rotation. Every 17 hours, the magnetosphere reconfigured itself, exposing different regions of the planet to the solar wind. It was as if Uranus experienced a magnetic storm every day. This constant reorientation had dramatic effects on the space surrounding the planet. Charged particles from the sun slammed into the magnetosphere at odd angles, sometimes penetrating deep into regions that would normally be shielded. The magnetail twisted and snapped, releasing energy in unpredictable bursts. Voyager 2 observed signatures of magnetic reconnection events, where magnetic field lines break and reconnect on a scale that rivaled, and sometimes exceeded, those seen near Earth. Uranus was not passively interacting with the solar wind. It was wrestling with it. For the scientists analyzing the data, Uranus became a puzzle with no clear solution. Was this magnetic configuration the result of the planet's ancient tilt? A byproduct of whatever catastrophic event knocked it sideways billions of years ago? Or was the tilt merely a coincidence, amplifying an already unusual internal structure? Some theorized that Uranus's interior was layered in a way that prevented heat from rising, starving the dynamo of energy and confining it to a smaller region. Others suggested that the planet's icy mantle, under immense pressure, might conduct electricity in ways never before observed. Each explanation raised new questions. What made the discovery even more unsettling was its implication for the rest of the universe. If Uranus could generate such a wildly misaligned magnetic field, then magnetism across the cosmos might be far more diverse than previously assumed. Planets orbiting other stars, especially those similar in size and composition to Uranus, could possess magnetic environments unlike anything seen in our solar system. This had consequences for atmospheric retention, radiation exposure, and even the potential for habitability on moons. Voyager 2's data transformed Uranus from an oddity into a prototype, a warning that nature was under no obligation to follow humanity's expectations. As Voyager 2 sped past Uranus and began to pull away, the magnetic readings did not settle down. They grew stranger. The spacecraft passed through regions where the magnetic field flipped direction abruptly, then smoothed out, then fractured again. The magnetosphere seemed to breathe, expanding and contracting in response to forces both internal and external. It was not a static structure but a dynamic system in constant flux. By the time Voyager 2 exited Uranus's magnetic influence, scientists were left with more questions than answers. Uranus had revealed itself as a planet defined by imbalance. Its rotation was sideways. Its seasons were extreme. Its atmosphere was quiet but fast, and its magnetic field, perhaps its most fundamental characteristic, was broken, displaced, and perpetually in motion. The ice giant had overturned decades of assumptions in a single flyby. Yet Voyager 2 was not finished. Beyond the planet itself lay a collection of moons, each orbiting within this distorted magnetic realm, each bearing scars of a history yet to be told. And among them was one world that would steal the spotlight and challenge everything scientists thought they knew about small planetary bodies. Chapter 4: Worlds Within Worlds, Moons and Atmosphere. As Voyager 2 continued past Uranus, attention shifted from the planet itself to its entourage, its moons, and the secrets hidden within its frigid atmosphere. Among the 5 major moons, none captured the imagination like Miranda. Once considered a small, unremarkable satellite, it now revealed a face fractured, jumbled, and chaotic, as if some cosmic sculptor had torn it apart and stitched it back together in pieces. Voyager 2's cameras returned high-resolution images of canyons deeper than the Grand Canyon, cliffs taller than any mountain on Earth, and surface patches that seemed almost incongruous with one another's, smooth plains abutting chaotic, crumpled terrains. Geologists and planetary scientists were baffled. What could produce such violent patchwork geology on a moon so small, so cold, and seemingly inert? The prevailing theory pointed to catastrophic events in its past, massive impacts that shattered its crust, perhaps even causing partial reassembly, combined with the slow creeping of ice through its interior over billions of years. Miranda, it seemed, bore the fingerprints of both destruction and strange regeneration, a world whose story was written in jagged lines and frozen scars. Yet Miranda was just the beginning. As Voyager 2's instruments scanned the surrounding space, the presence of smaller moons, previously undetected, began to emerge. These tiny satellites, some no larger than a few dozen kilometers across, wove a complex dance around Uranus, shepherding rings, influencing orbital resonances, and offering clues about the planet's history. Each new moon added depth to the narrative, suggesting that Uranus's satellite system was not a static collection, but a dynamic, evolving ensemble. Some moons might be remnants of larger bodies broken apart by collisions. Others could be captured objects wandering the outer solar system until trapped by Uranus gravity. Together, they painted a picture of a planetary system in constant negotiation, a web of gravitational relationships as intricate as any clockwork mechanism. While the moons offered a story of violent history, Uranus's atmosphere told a subtler, colder tale. Unlike Jupiter's and Saturn's thick, turbulent envelopes, Uranus's atmosphere was frigid, almost lethargic, with temperatures plunging below -350 degrees Fahrenheit, composed primarily of hydrogen and helium, with traces of methane giving the planet its cyan hue. The atmosphere displayed surprisingly complex cloud patterns, despite the low energy available from the planet's interior. Voyager 2 observed faint bands and streaks indicating slow, steady winds circulating around the planet at hundreds of miles per hour. The planet's extreme axial tilt meant that solar heating was distributed unevenly, yet the atmosphere managed to maintain stability. Unlike its larger siblings, Uranus had no internal heat source sufficient to drive massive storms, a peculiarity that set it apart and highlighted just how unique ice giants truly were. Even the rings interacted subtly with the moons and atmospheric dynamics. While Saturn's rings dominated the imagination with bright, icy brilliance, Uranus's dark rings cast subtle shadows, guiding the motion of tiny satellites, and perhaps influencing the transport of dust and ice across the system. The interplay of rings, moons, and atmosphere suggested a system finely balanced, yet precariously arranged. As if Uranus's tilt and unusual magnetic field had left their mark not only on the planet, but on every object orbiting it. Miranda's fractured planes, the hidden moons, and the subdued but intricate atmospheric patterns all hinted at a past both violent and mysterious. Each piece of data gathered by Voyager 2 reinforced the sense that Uranus was more than a planet. It was a laboratory for extremes. It showed that planetary systems could evolve in unexpected ways, that small bodies could endure cataclysm and reassemble, that atmospheres could adapt to extreme orientations without descending into chaos, and that the tiniest moons could play outsized roles in maintaining balance. In essence, Uranus and its moons demonstrated that even worlds once dismissed as bland could harbor profound surprises, forcing scientists to expand their understanding of what a planet or its satellites could be. As Voyager 2 moved beyond Uranus, sending back every remaining bit of data before disappearing into the depths of space, the legacy of these moons and atmospheric discoveries became clear. They provided a blueprint for understanding ice giants not just in our solar system but across the galaxy, particularly as astronomers began identifying exoplanets with similar size, composition, and distance from their stars. Miranda's scars, the hidden moons, and the frigid atmosphere were no longer just curiosities. They were critical evidence that planets, like stories, could hide their most dramatic chapters beneath a calm exterior, revealing complexity only to those bold enough to venture close. In the end, Voyager 2's Uranus flyby showed that even the outer solar system, so distant, so quiet, so cold, was brimming with lessons about planetary formation, evolution, and survival. The moons and atmosphere were more than companions to the planet. They were co-authors of Uranus' strange sideways narrative, and they set the stage for the final chapter of this mission, the enduring legacy of the ice giant and the questions that remain, still waiting for humanity to answer them. Chapter 5: Legacy and Future, the Ice Giant Blueprint. Voyager 2's encounter with Uranus was not just a fleeting glimpse of a distant planet. It was a defining moment in humanity's understanding of ice giants. The spacecraft's instruments had returned an unprecedented wealth of data: a tilted, rolling planet, an off-center magnetic field, faint yet structured rings, moons scarred and stitched together, and an atmosphere cold, subtle, and strangely self-regulating. Each discovery challenged assumptions, forced new theories, and demanded that scientists rethink what a planet could be. Uranus was no longer a pale, unremarkable dot in the night sky. It was a blueprint, a laboratory, a cosmic paradox whose lessons would reverberate for decades. The immediate impact on planetary science was profound. Voyager 2's observations of Uranus redefined the category of ice giants. Jupiter and Saturn could be understood as massive, well-behaved gas giants with familiar storm systems, deep heat engines, and largely symmetrical magnetic fields. Uranus and its sibling Neptune, by contrast, were smaller, colder, and far stranger, with magnetic fields that defied conventional models and atmospheres that lacked internal heat. The spacecraft had shown that planetary classification was not merely a matter of size or composition, but also of dynamical complexity and historical contingency. Any future models of planetary formation now had to account for catastrophic collisions, axial tilts, and the possibility that magnetic fields could arise in unexpected ways, offset and misaligned, creating environments far more intricate than previously imagined. Voyager 2's Uranus flyby also cast a long shadow forward into the search for exoplanets. In the decades since, astronomers have discovered thousands of planets orbiting distant stars, and a significant number resemble Uranus more than Jupiter. Hot ice giants, cold Neptunes, and other variants bear testament to the diversity revealed by Voyager's singular mission. Uranus became a reference point, a concrete example of how a planet could exist in ways that challenge intuition, reminding scientists that observational models built on the solar system alone were incomplete. Studying Uranus' moons, rings, and magnetosphere provided vital clues about how such worlds could maintain stability despite extreme tilts, faint internal energy, and chaotic magnetic configurations, shaping the way researchers evaluate the habitability, evolution, and potential for life on distant exoplanets. The magnetic enigma in particular continues to influence research today. Uranus's off-center field has prompted ongoing studies into planetary dynamos, the role of layered interiors, and the behavior of electrically conductive ices under extreme pressure. Every simulation, every lab experiment, every model now considers the possibility that what we see on Earth is not universal. The implications extend beyond Uranus itself, touching our understanding of space weather, auroras, magnetospheric interactions, and even the shielding of moons or potential atmospheres on exoplanets. Voyager 2, in effect, gave scientists a template for exploring worlds far beyond the reach of human spacecraft. Voyager 2's journey also highlighted the enduring value of exploration and serendipity. Uranus was not a primary objective when the spacecraft launched. It was a bonus, a cosmic detour made possible by a rare planetary alignment and precise navigation. And yet, this bonus became one of the most consequential planetary encounters in history. It demonstrated that opportunities in space exploration are fleeting, that the universe often rewards those who are prepared to follow the path of curiosity, and that even worlds once considered dull can harbor profound mysteries waiting to be uncovered. Looking forward, the legacy of Uranus is not static. Missions to the outer planets are now being planned with Voyager 2's data as a guide. Scientists envision orbiters, atmospheric probes, and even landers for moons like Miranda that could unlock secrets only hinted at by the fleeting flyby. Understanding Uranus fully may require decades of new technology, patience, and ingenuity. Yet the excitement is palpable. Voyager 2 proved that the ice giants are laboratories of extremes, that they contain histories written in ice, rock, and magnetic fields, and that each discovery reveals the universe's capacity for surprise. And so the story of Voyager 2 and Uranus is both a record and an invitation. It is a record of human ingenuity and perseverance, of machines venturing into the void and returning with truths that reshape our understanding of the cosmos. It is an invitation to look beyond the obvious, to question assumptions, and to explore the uncharted reaches of space where planets roll sideways, magnetic fields twist in unexpected ways, and moons wear the scars of billions of years of cosmic history. Uranus remains a world of mystery, a puzzle incomplete, a challenge to the next generation of explorers. Its secrets are far from exhausted, but thanks to Voyager 2, we have a map imperfect, tantalizing, and awe-inspiring of a planet that broke the rules and showed us that the universe is far stranger and more beautiful than we ever imagined.